Thanks for the introduction, and it's a pleasure to be here. Thank you for inviting me. So this is a topic that I chose deliberately, and tell you why. There is a story behind it. So this is this thing called branching random walks, which arise naturally in various disciplines, and I'll tell you some story about that. But why I chose this talk, nothing else. So this is essentially a walk. So is it too close? It's always up. So this is a walk with a student of mine, Ayan Bhattacharya, who was a PhD student at Indian Statistical Institute, and a colleague of mine, Rajat Shubhra Hajar. I'll show their pictures in the end. Okay, so why I chose this topic? So once I was traveling by a train, and at that time we were writing a paper based on this work. And I had a draft of the paper and I was correcting it. And then there were two students who were sitting opposite to me in the train, and they got curious. They were students of class 12, I think, they told me later. So they got curious. They asked me what I am doing. I said, I'm just correcting, this is a paper. So initially, they didn't really understand what is going on. After some stage, they got really excited. They said, you're proving a new theorem. I said, not really, to be honest, it's a theorem already some people proved. I'm just making a little bit of improvement. But I could see the excitement in their eyes, that, I'm proving something new, perhaps. So that sort of motivated me that, one thing that we never do as mathematicians is that we never tell people what we do. People know what, say, scientists do, say chemists. You know that they take a red solution and a blue solution, they mix it up and it becomes green suddenly, right? That's what chemists do. What do we do as mathematicians? What we do is we take a red theorem and a blue theorem, we mix it up, and then we make a green theorem. That's our job. So I'm here to try to tell you what we do, rather than exactly what we did here. Okay? So that's why I chose this topic. And the students who were there and got excited with this, that we are proving something new, were almost your age. So therefore, I chose this topic. Okay, so I'll use something that Swati has already used. So thank you for introducing that, namely the number line. That's nice, thank you. So, by the way, typically whenever I start a talk, I ask two questions, especially one question is, can you hear me from at the back? I know that here I don't have to ask because there is a microphone, but if I'm too loud, let me know. Because I have a habit of shouting, and already there is a microphone, so there might be a double effect. So just say that you're too loud. Siva is not allowed to say. Okay, so there is this term branching random walk. So I'll first start with what is called a random walk. Okay. So the word random essentially means there is something that depends on chance. There is a chance involved somewhere. So what is a random walk? So this is the simplest possible model for random walk. So this is the number line, as I said. Swati has already introduced this to you, and I didn't realize that we saw a number line so far back. I was thinking of class 7, but you're right. I mean, in the scale, there is a number line already. Except that in the scale, there is no negative number. Okay, so I do need the negative number. You'll see why very soon. Okay, so I have a person, a completely crazy person, who's standing on number 0 on this line. Okay. So person is here, standing like this. Now what that person does is that he or she tosses a coin, and if the outcome is head, he or she will take a step forward like this. Or if the outcome is tail, he or she will go backward like this. Okay? And I make an assumption. I assume that the coin unbiased. What do I mean by unbiased? I mean that probability of head and probability of tail, they're equal. Okay? Now you would say, why? All coins are unbiased. Why do you have that assumption? So I have this question that I always ask people, and it's, let me see how many of you have seen. Have you seen the movie Sholay? How many of you have seen the movie Sholay? Let me see. Not bad. Yeah, okay, good. So there, if you haven't seen it, please see it. Okay, it's a very good movie. Amitabh Bachchan uses a coin that has two sides, head. So it's a biased coin. There is no tail. Right? Tail is not even possible. So therefore, there are bias coins in real life. Okay, Sholay is not real life, but close to real life. So therefore, you have to make that assumption. So make the assumption that you have two sides, head and tail, and more importantly, they have equal chance. You have equal chance of getting a head and a tail. Okay. So with that assumption, you toss the coin. Suppose first one is a head, so you move to +1. Not you, sorry, the crazy person. You're not crazy. Okay. Again, the coin. Suppose again the crazy person gets a head, so he or she moves again to the +1, so it moves to +2. Now suppose it's a tail, so moves back, takes a step -1, which means moves towards the left, which is goes to 1. He or she goes to 1. Again, suppose it's a head, so goes to 2. I won't bore you too much. So again, say it's a tail, it's 1. Tail, now it's a 0, then -1. Now that's why I need the negative part of the real line. -2, again a tail, and so on. I'll just stop here. You understood the dynamics, right? Every time you toss a coin, wherever you are, wherever the crazy person is, if it's a head, that person takes a step towards right. If it's a tail, that person takes a step towards left. That's the idea. So let me write it in words. Note that we really didn't need the entire real line. We just needed the integers on the real line. That's enough, because every time it's a plus or -1 step. So the crazy person is always going to be on integers. Okay. Now let me write it down in words. So first you start, okay, the crazy person starts at 0. He or she tosses a fair coin. Fair coin means unbiased coin, which means head and tail are equal probability and both are half. So if head appears, take a step +1. If tail appears, then take a step -1. I just said that. Now toss another fair. You can toss the same coin, but toss in an independent fashion. What do I mean by independent fashion? I mean that second time, the output, head or tail, should not depend on what was the output last time. Don't do the following. So last time there was a head, so this time I should get a tail. So you toss it in a way that you get a tail. Don't do that. That's what I am saying. Okay? It should be completely independent of whatever happened before. Okay. Again, you do the same thing. If head appears, you take a step +1. If tail appears, you take a step -1. Okay? So this is you just have to repeat these two steps over and over again. This gives what is called a simple random walk on integers. Why is it called a random walk? Because there is a randomness involved. Every time, whether you take a +1 step or a -1 step, depends on chance. There's a half probability of going towards right, half probability of going towards left. By the way, I'll share these slides. You can just share it with everyone. Oh, okay, that's fine. Also share the slides. Yeah. Okay. Okay, so that's why it's called random walk, and it's of course a walk because the crazy person is walking on this number line. It's called simple because you're keeping it very simple. That's why. You're just allowing the person to either take a step forward or backward or right or only one step at a time. You can make it more complicated. What you can do is you can call it any random walk. What you do is the following. For every integer, you fix a non-negative real number pi such that their sum is equal to 1. So what you do is you have integers, right? You have all these integers. On every integer, you put a number, non-negative number, okay? Either 0 or positive number, so that the numbers add up to 1. So these numbers will be probabilities, as you will see. What you do is start at 0, same thing. Take a step I with probability pi. So first time, instead of just taking +1 or -1, now you're allowed to take any step, but the probabilities are different. Okay? You take a step 1 with probability p1, take a step -1 with probability p-1, and so on. They add up to 1, so you have to take one of the steps. Okay. Again, once you reach somewhere, you take, I should not be saying you should be saying the crazy person is somewhere. He or she takes another step j with probability pj in an independent fashion. Again, one has to forget whatever has happened in the past and take a step. Okay? So repeat this again and again. This is the more general form of random walk. So if you see, in case of simple random walk, what I allowed is I allowed p1 to be half. So taking a step towards +1 was half. p-1 to be also half. So taking a step towards -1 was probability was half. And then all other pi's were 0. So you cannot take any other step. In general, you can have more other possibilities also. Okay. Now, what is a branching simple random walk? So far we have only talked about random walk. Now I will talk about branching random walk. So I need to draw a picture. I think this is an ideal place for that. This is 0 in the number line. You have 1. Now you don't have a crazy person, you have a crazy particle. So what the particle does is, first, the particle starts at 0, just like the crazy person. Next moment, the particle divides into 2 particles. It branches into, that's why the branching comes. Okay, so it branches into 2 particles, and each of them make a step either +1 or -1 independently of each other. Okay, suppose it broke into 2 particles. So this is 0, this is 1, this is -1, and so on. So it broke into 2 particles. One of them came here, another one came here. So you see, here there was 1 particle, now you see 1 particle here, 1 particle. Okay, that was the first step. Is the dynamics clear? What's going on? Every time, I'm going to write it down also nicely, but every time each particle is getting divided or branched into 2 particles. You can either think of it as a particle or think of it as a bacterium that breaks up into 2 bacteria, and both the bacteria makes a movement either towards +1 or -1, completely independent of each other. Everything is independent. Nobody sees what else others are doing. That's what it means. So this goes on, this procedure goes on. So I can show you in a movie like what happened exactly. So it started like this. This is the movie. And what you see here, I will call it a snapshot. It's like the movie is going, at a time I'm taking a picture. With cell phones, these things, people know exactly what this means, so I don't have to explain it well. Okay, so what is the, in words, what is happening? So you start with 1 particle at position 0. I'll call it the 0th generation. So let me name them. So this is the 0th generation. 0th because this is where I start, so I call it 0th. This is the first generation. This will be the second generation, and so on. And this will be the third generation. Okay. So the particle branches into 2 particles. Each new particle, think of it this way, each new particle tosses a fair coin independently of each other and takes a step +1 or -1 depending on whether the head or tail appears. So exactly in this case, for example, there were 2 particles, one got a head and another got a tail, so they go 2 different ways. Here both got head, so that's why both went here, and so on. Okay, so this gives you the first generation. So you get the first generation, and then each particle repeats these steps independently of each other. So everything is forgetting what else others are doing, and this is going on. So this process is going on. This gives you what is called a branching simple random walk. Again, why is it simple random walk? Because each particle, if you just look at one particle here, it's giving you 2 particles, and each of them is making a simple random walk, either going to the +1 or -1 with equal probability. So that's why it's called branching simple random walk. So it is like random walk, but you have an additional thing which is branching. That's why it's called branching simple random. That's why the name. Okay, now you can again complicate this guy. Just like random walk, we started with +1 and -1, and then we said, okay, any number of states allowed. Okay? You can jump from 0 to 30 or anything. Okay? Similarly, you can do the same here. So what you can do is, you can call any branching random walk in integers. So what you would do is, you would do the same thing. You will have for every integer I, you fix a non-negative real number pi in such a way they add up to 1. Okay? So this will give you the probabilities of the particles moving. So start 1 particle position 0. This is the 0th generation. Now the particle branches into 2 particles still, but both the particles independently of each other takes a step I with probability pi, and this goes on. So it's the same thing except that now the particle can move farther. Okay, not just +-1. That's the only difference. Okay, is the model clear? Before I move on, is the model clear with the picture? And so now let's see what we have to do with this model. By the way, I just remind you that if you take P1 and P-1 to be half and all the other Pi's to be 0, just like previous case, you'll get back the branching simple random walk. So always keep that in mind. If you forget this looks too complicated, always keep this picture in mind. That's good enough for us. Okay. Now, so far as I said, I only needed the integer line. Right? I never needed the real line to be. Now I'll need the real line. What I'll do is, I'll do everything the same except that the step sizes, there is no reason the step sizes should be integers. I can allow them to be 2.5, 3.7, pi, e, everything. Okay? Any step is possible, suppose. So that will make it a branching random walk on the real line. And if you think of real lives, if you have bacterium, there is no reason why the bacteria will always take an integer step or a particle. It may actually go any step. So therefore, instead of making it integers, I'll make it any real number. But the number will still be random in some way. So let's just remember this much. That should be good enough. And also, one thing to notice, these particles, these two particles are called offsprings of this particle. These two one are offsprings of this guy, and so on. So therefore, this each time every particle is producing two offspring particles. But that can also be made 3, 4, or anything else. Or we can even make it random. It can be 5, it can be 4, it can be various things. So this also can be done. But don't worry too much about this. This model is good enough. If you just think of this model, that should be good enough for us. Okay, now what we are interested in, first I'll tell you this. So this model was introduced in the 70s by these three mathematicians, Hammersley, Kingman, and Wiggins. And there were a lot of other works afterwards, but it's basically this model was born in the 70s, 74, 75, that time. Okay, now why is it important? I mean, why would somebody consider such a model? Now this is important because of the following. So this appears in many contexts ranging from biology to statistical physics. So there is a branch called statistical physics, which is basically an intersection of physics and statistics. So today you have learned some statistics, right? So this branch actually writes, it talks about physics and then look at statistics of that. So that's why it's called statistical physics. Now, why is it so important? For example, biology, it's clear because it can be one bacterium which is moving in this line, which is, producing more bacteria and then moving in a line. So that's natural that it can appear in biology. Similarly, physics, because this can be a particle. So in general, it can be used to describe how a growing population of anything that you can think of invades a new environment. Okay? It can be spiders, it can be anything else. So therefore, this is an important model. Now, what we have done is we have made it very simple in the sense that we have allowed particles to move only along a single line, or initially to start only on integers. Okay? So the particles or the bacteria, they're moving only on a line. That's a very simple model, but simple models are always good to start with. Then you can move to more complicated models. For example, you can let the particles move in a plane. So it's 2 dimension, as Swati was telling. First start on 1 dimension, then, so I'm going even below you. So you started from 2 dimension, I think, right? So start from 1 dimension, then you can go to 2 dimension in a plane. Then you can go in the whole room, you can have particles. So you go to the 3 dimension and so on. But for this talk, I'll just, restrict ourselves to the simple model. So namely, everything is happening in a line. And we'll be interested in what is called a long run configuration, this red phrase that is there, this italic phrase of the positions of the particles. Now, what do I mean by long run configuration? So this is what I'll be interested in. So I should explain what that means. So as I said, I'll just go back here. This movie that was there. Yeah. So the movie started with 1 particle, then it became 2, then it became 4, became 8. This is 8, right? And so on. So in the nth stage, therefore, you will have many particles? 2 power n many particles. Okay? And as you can see in this movie, that the particles are spreading because some particle or the other will hit this 3 and then it will go to 4 and so on. If you go on playing this movie over and over again, you will need bigger and bigger line. So that's exactly what I mean by long run configuration. So what do I mean by that? So let's go back. going too fast. So what is long run configuration? So long run configuration is following. So just quickly recall this is a growing collection of particles which starts from a single particle and then branch and spread independently of their positions. Okay. Now, if you let this dynamics run for very long time, so if you go on doing this, go on making this picture, of course this board won't fit it, but you go on doing that, and you look at it as a movie, and then you suddenly, after say 1 million generations, you take a snapshot. How would it look like? That's the question. Now, of course, this question has to make sense because after 1 million generations, the points will really spread out a lot. So therefore, in order to make any sense out of it, what we'll do, we'll compress the whole picture. Okay? So the whole picture is spread out, so we'll just compress it like this so that we can see it. Now I'll ask, how does it look? Okay? So this is the question that I'll be asking. Now this is a very important question because this is very important in physics. For example, certain, if you have particles in a room and whether certain physical phenomena will happen or not will depend on the long run configuration of the particles. Okay? Similarly, mathematical biology also this is important because if the bacteria, if they die out, if they don't stay, too many bacteria go to one side of your body, then there might be some disease. If not, it's well spread out, there won't be any disease and so on. So it's definitely very important. And of course, this whole model depends on chance and therefore probability theory is important also. So therefore, this is a very important question. Now this is the real title, the second part of the title, the 2 conjectures, 2 theorems and a question. Again, this again is motivated by a movie. Can anyone guess which movie? Any guesses? It's okay. An English movie, that's a hint. It's a British movie, that makes it a bit better. Come on. Sorry? No. Exactly like this. 4 weddings and a funeral. Have you seen it? Has anybody seen it? Please see, it's a very nice movie. I have a friend who has written a paper that has titled 4 Theorems and a Financial Crisis. I think that's cool to be able to write such a paper. Okay, so that's why I could not write such a paper, so at least use it in the title. Thanks for giving the opportunity. Okay, so what are these conjectures? So what does the word conjecture mean? Do you all know what conjecture means? Yes. Okay, very nice, very nice. So something that you guess, like exactly what Swati was doing, right? Swati was finding a pattern and then making a guess, and then she was proving it. She was just stated something and then asked you to check. She said, don't believe the mathematicians. That's very important. Don't believe, just check. So conjecture is something which is a guess, but I would say it's not just a guess, as she said. You already see a pattern, so it's an educated guess. You make a guess on some pattern, and then somebody wants to later prove that. So there are 2 conjectures about this long run configuration of the particles, and they were made by 2 famous statistical physicists, Brunet and Derrida, in 2011. So what they said is that the long run configuration of the particles is what is called a decorated Poisson point process. So don't worry about these words, just let them remain. I'm not going to explain you these things, so don't worry. Okay. And it satisfies or exhibits what is called a superposability property. Now I'll tell you what superposability property means in a very qualitative language. So suppose I start with such a branching random walk, and I run it for a very long time. So after many generations, I see it, I take the snapshot, and then I have decided that I won't see the whole I'll see the snapshot, but I'll rescale it so that it's within this size. So I'll do that. Suppose I do that, I look at that picture. Now I ask one of you to do the same. You start another branching random walk, again run it to million generations, again take a snapshot, but then again reduce it to this kind of size, same size as what I had kept here. Now you superpose these 2. That's why the superposability word comes in. What you see is you have a picture, you have another picture, you superpose these 2 pictures. And superposability means, roughly, is that if you superpose these 2 pictures, qualitatively you won't be able to see any difference. It's going to remain the same qualitatively. That's what superposability means. So they had conjectured, of course, it was not just a conjecture, not just a guess, as she pointed out, it was an educated guess. So they saw some patterns using some examples. They made this conjecture that it will have this superposability property, and then they also said that it will be what something called decorated Poisson point process. I am not going to describe what that means. Okay, so then they also asked another question. The question was, in the same paper that they wrote in 2011, they asked, are these two the same? In the sense that superposability property will hold if and only if the point configuration is what is called the decorated Poisson process. So that's the question they asked. And then in 2013, this French person, pronunciation is Maya. It's not Maillard, it's Maya. I was told by somebody French, but I don't care because they can never pronounce my name correctly. Okay. So I'll just say Maillard. Okay. So Maillard in 2013, he proved that Pascal Maillard, he proved that they are under some conditions. He had some conditions. I'll tell you roughly what the conditions mean. And later, in 2017, Madul, again another French person, Thomas Madul, he actually proved using the work of Maillard that 1 and 2 are actually, both satisfied by under the same conditions of branching random. So now you have two conjectures, two theorems, and a question. But I would say this is not a question anymore because this has been already answered under some conditions. But it's still a question because what if these conditions are not satisfied? There are some conditions under which they could prove certain things, but what if these conditions are not satisfied? So the key question is the question, but apart from the question, when the Maillard-Madule condition doesn't hold. Now what kind of conditions? What do we mean by that? So let me tell you the condition. So roughly speaking, the condition of Maillard and Madul was, it says that, think of this first time this random walk was happening. So first time I said it's either +1 or -1. You can only take a step of +1 or -1. Then I said you are allowed to take a size of 30 also. But what Madul and Maillard said is that no, you're really not allowed to take very big steps. You have to take reasonably small steps. In the sense that you might take a step of size 100, but that will happen only 1 in a million. Or you may take a step of size 1000, but that will happen very, very, very rarely. If you do it only many times, you will see only once. So most of the time, you will take very small steps. So that's what their condition means. Okay? So most of the time, you are going to take very small steps. If you assume that, then these two conjectures were proved. And the same condition showed that these 1 and 2 are equivalent. This being a decorated Poisson process, whatever that is, don't care. And the superposability, whatever I said, you take two pictures and superpose and you won't be able to see the difference. This was proved. Now the real question is, the key question is, what if we allow big step sizes? What if I say that one can actually take a step of size 1000 with reasonably high chance? So, reasonably often you will see a really big step. Then of course their method will fail. So when my student Ayan came to me for his PhD, so I gave him this problem. I said, why don't you try this, in the other cases? And then what happened is the following. So let me just sort of summarize what was there. So there was this decorated Poisson point process, whatever that is. And then there is the superposability, which is another box. And then Brunet and Derrida asked that whether these two are equivalent or not. That's why I have these question marks here. And they said that, branching random walk should satisfy these things. Now, suppose you have small step sizes and you want to make it big. What is one way of doing it? There are many ways of doing it. I mean, I'm looking at something very specific. Let me ask you the reverse question. Suppose you have a very big number. You want to get a small number out of it. What can you do? You can take a square root, for example, or you can take half it. Log. Log is another thing. That's the word I was looking for. Thank you. Whoever said that. Thank you. So you can take log. Similarly, if you want to make it big, what can you do? What is the reverse procedure? Exponential. So therefore, suppose the step sizes are just like Maillard and Madul, but what I do is I don't look at the step sizes just like that, I exponentiate them. In other words, if Maillard was taking a step of size 3, I'll take a step of size, say 2 power 3 or something power 3. Now this will automatically make it very big, because suppose Naolekar was taking a step of size 10, I'll already take a step of size 1024, 2 power 10, that's quite large. So you see it's going to be large. So therefore by exponentiating, it's seen that this whatever they call superposability changes to something known called stability. I'm not going to explain what it means, but again, there are too many vague words I'm saying, but it's just obtained by exponentiating the step sizes. It's just making them bigger, because we want bigger step sizes. Similarly, if you play the same game on what is called decorated Poisson point process, we discover that it goes to what is called scale decorated Poisson point process, something that is already seen in the literature. And interestingly, Davidov, Molchanov and Zuev, in their papers in 2008 and 2011, the first paper 2008 actually, they had proved that these two are actually same. So this happens if and only if this happens. So therefore, by exponentiating and taking log, one can actually answer the question of Brunet and Derrida using their method. I'm just pointing out in a very vague fashion. So you first start with one of them, you exponentiate the step sizes, you use this equivalence and then go back by taking log. This is one of the proof of these two are equivalent. Very rough way of proving, but however, Maillard gave a different proof. His proof was very different. He used a different technique. Now the point is, what is the upshot of this picture? The upshot of this picture is that when the step sizes are big, so that you can think of them as exponentiation of whatever earlier was happening, then you should not, your keyword should not be superposability, it should be stability. And your final configuration should not be a decorated Poisson point process, it should be what is called a scale decorated Poisson point process. Now I'm not explaining you these things, but always think of them as whatever was before, you are just making the step sizes big by exponentiating them. Okay. So then the conclusion should be this. In our setup, this DPPP, this is a standard acronym, by the way. I should not call it acronym, standard short name that physicists use. This should be replaced by SCDPP, which is called scale decorated Poisson point process. And whatever I was calling superposability should be replaced by stability. And then under this change, we could prove that these conjectures hold, both of them. And we could also explicitly compute the long run configuration. There is some mathematics behind it which I am not saying, but we could explicitly compute, which is actually missing in the Maillard module setup, because their step sizes were small and then they could not actually explicitly compute it. They could only show that there is such a configuration. They could not compute exactly how it looks like. Okay, so now I would like to introduce you to my collaborators. So this is my student Ayan Bhattacharya, who is now doing a postdoc in Amsterdam. Really cool place to be. And this is my colleague Rajat Hajra, who is in Kolkata, ISI Kolkata. Since there is time, I would like to end with another story. I think then I'll ask you to ask me questions. So what happened is that when I first gave this problem, so one of the important things that you can see here is, for example, if you look at this, the rightmost particle in this generation is at 1. Okay? Here the rightmost particle is at 2. There are 2 such particles, but the rightmost is 2, and so on. There was a question about rightmost particles, and we thought that that would be a natural question to first ask. If you look at the picture, in every generation, you take a snapshot after say million generations. Where is the rightmost particle? How far is it from 0 on the average? So we wanted to ask that question. And then I asked Ayan to make some calculations. He did a lot of calculations, and under some special assumptions that was going away from Maillard and Madhu, we could finally prove that. We could calculate how it's growing and so on. We could prove some results. And then we are very happy. We were trying to type up the paper and so on. Then suddenly one Sunday, I was looking into some literature, and I found out that in 1979 actually, somebody has already done it. Rick Duret has done it already, somebody. And then I was really upset. I first emailed Ayan and Rajat and told them, bad news, whatever we did is already done. It's very sad. Of course, it was good that, our calculation and their calculation are matching, but I was very upset. And then at that time, our milkman had come and wanted to deliver milk. So what he did is, so we didn't take, so at that time we used to take the cow milk. So we'll take a vessel, give it to him, and then he'll pour and so on. It's not the packeted milk. So he called, and then I said, okay, I'll give you the vessel. But I was so upset that I totally forgot about him. And I'm not sure if the milkman was a mathematician or not. He also didn't do anything. He didn't ring the bell once more. He just waited and waited. After some time, he gave up and left. I totally forgot about that milkman. And in the evening, suddenly when I was going to make tea, I saw that there is no milk. And I realized that, this is what happened. I called the milkman. He said, sorry, I waited, and then I went back. So whenever I talk about this incident, I talk about this work, I tell people that, even if you do a calculation, it was done already, and we were very upset. But still was a very good experience for us, because in the end, of course, then I also called Ayon and Rajat, even before realizing the milkman had left. I called them and told them, this is what it has been done already and so on. But what was interesting is the idea that we had for tackling this also helped us to get to these conjectures, to solve these conjectures. So therefore, if you do a calculation and you see that somebody else has done the same calculation, you should actually be happy. You should immediately take the milk from the milkman. You should not make the milkman waiting. Okay, so that's where I would like to stop. So I think it has been a long day for you, so I would like to stop early, and I also have to leave early, so I think, yeah.
Sir, like this is a mathematical model. So, what is the motivation behind making such mathematical models, or what is the physical significance of doing all these things, taking probabilities and everything?
As I said, this comes from actually physical things. For example, growth of particles and so on. Suppose you have, so instead of this, suppose you have in a box, you have one particle, and then the particle produces more particles and it grows up. The whole system, the particles invade this environment. Now, one of the questions that can be asked is, suppose a lot of particles, this can be very important in, say, chemistry or physical chemistry. So a lot of particles go to one side of the box, then some explosion may happen. So therefore, one needs to know what happens eventually. The particles, they spread evenly, or they go to one side of the box, or so on. So that's why it's important. It comes from physics, actually. This model comes from physics and biology. So it is actually a physical model, which we are making it mathematics. We are mathematicizing it so that we can prove some results about it. But at the end of the day, this paper of Brune and Derrida, if you see, it's a completely physics paper. They talk about particles and how they branch and so on. Motivation is from physics.
Has there been any extrapolation of this model to 2D or 3D? Because
yes. There are. I'm not talking about them. They are more complicated. I'm not as brave as Swati. I remained in one dimension. No, but yes, there are extrapolations to higher dimensions, and there things become a bit more complicated because you have directions, various things to control, and so on. Yes, same questions can be asked. What is the long-run configuration of the particles, and whether it satisfies this kind of superposability or not? And people actually have answered that also.
And one more question, like, does it explain or give the probability of something that we observe is happening in the system? And this model, basically, its significance is that it gives us the probability of that particular event which is happening. So, does it give the probability?
Yes. So, essentially, in other words, what you are saying perhaps is that suppose you actually observe a physical system, and does it match that system, right? Is that what you are asking? Or no, I'm sorry, can you ask the question again?
I am asking, like, we know what is the initial state of a system is.
Right.
After some time, we observe a particular state of the system.
Right.
Let's say some of the particles are at some place or someplace. Right. So is this model all about telling the probability of that particular state being achieved?
Yes.
Okay.
For example, from here you can calculate. I can ask you, what is the probability that this particular setup will happen in the third generation? You can actually calculate. In fact, there are two ways of having this configuration coming in the third generation. I leave it as an exercise to find out. I showed you one of the ways. There is another way of coming to this. So you have to find the probabilities of both and then add them up and so on. So yes, the answer is yes. Anyone else?